Hello sir, I am RUSHIKESH. We are choosing the project Stealth Satellite. In this project, we are working on the problem statement, the design and development of the multispectral and the stealthy reconnaissance satellite, which is consecutive to be photo reconnaissance satellite, where the satellite is capable of suppressing its laser, radar, visible and infrared signature, ensuring both the operational effectiveness and the reduced detectability. The objective for this project is to engineer a satellite that integrates advanced stealth technology and material, enabling it to operate covertly while fulfilling its intended mission requirement. The satellite must exhibit the following characteristics: laser signature suppression. The satellite should be designed to minimize or eliminate its detectable laser reflections, absorption, and the scattering to avoid detection by laser detection system. Radar signature reduction: the satellite must have the minimized radar cross-section to reduce its detectability by radar system, ensuring stealthy operation in both the active and passive radar environments. Visible signature minimization: the satellite's visible light emissions, reflection, and contrast must be reduced or controlled to make it less visible to optical surveillance and the tracking systems. Infrared signature management: the satellite should be equipped with the thermal control mechanism and material to manage and reduce its infrared emission, thus minimizing its detectability by IR sensors and thermal imaging systems. Deployment: the satellite will be deployed in the low Earth orbit for clear operation. The satellite will be used as a spy satellite.
Hello sir, I'm Shane and I will be explaining the design part of the satellite. So since it is working as a stealth satellite, we have chosen the top part of the satellite as a cylindrical cone, which will help to deflect all the radio waves coming from the enemies to a certain extent. We have chosen the top part of that is a cone and the below part that is a flat plate as massless, and the the middle part which is made up of a hexagonal cylinder in the CAD model, but we have chosen it to be a cuboid to for the ease of our calculations. The material which is going to be placed at the top part of the satellite, that is a cone, it should be capable of absorbing and diverting all kind of electromagnetic radio waves. Also, there are small thrusters which have been added to the cylindrical part of the not the cylindrical, the hexagonal part of the satellite to help the satellite to change the orbit and perform maneuvers. These are the 3D satellite views which you have made. So yeah, so the as you can see, the main body part of the satellite is a hexagon, but in our calculations we have chosen it to be a cuboid for the ease of our calculations in the moment of inertia, which Raj will be explaining in the next slide.
Good morning, sir. My name is PRERIT. I'm going to explain the mass movement inertia metrics for the part that Shani just now presented. So we have taken the main body to be as cuboid because to get the A, B, C relation. Because for the cylindrical part, we are not getting the proper relation as given in the bottom part, that I by y is greater than IXS is greater than IZZ. So I by y is written like this, I by y written like this, IZZ written like this. So we are getting that L is greater than H and W is greater than L. So we have assumed that H to be 15, L to be 10, and width to be 8. And then we have calculated our mass moment inertia matrix.
Hello sir, my name is Siddhant. So we go to the control strategy. The plan is to use a closed loop control system with 3 sensors: gyroscope, accelerometer and magnetometer. We can see GS, which is the transfer function of a PID controller, which describes how the controller responds to changes in the error signal, which is the difference between the desired set point and the actual process variable. The transfer function of a PID controller can vary depending on the specific implementation and tuning parameters. We see GS is equal to Kp, which is the proportional gain, plus Ki, which is the integral gain, upon S, which is the Laplace variable, plus Kd, which is the derivative gain, into S. Then we move on to the gyroscope. The gyroscope measures angular rate. In an ideal scenario, the transfer function can be represented as a first-order system with a constant gain and a time constant. Gyroscopes measure the rate of rotation around a sensitive axis. Their output is typically in units of angular velocity. The accelerometer. The output of an accelerometer is typically proportional to the acceleration applied to it. In the frequency domain, it can be represented as a constant gain within its operating frequency range. Accelerometers measure the specific force acting on the satellite along its sensitive axis. Magnetometers measure the strength and direction of the magnetic field. Magnetometers provide information about the local magnetic field vector. They are often used for attitude determination and orbit control, particularly in conjunction with magnetotorquers. Sun sensors. Sun sensors detect the direction of incident sunlight. The transfer function can be simplified as a linear relationship between the incident light intensity and the sensor output voltage. Sun sensors provide information about the direction of the sun relative to the satellite's body frame. They are often used for attitude determination. Here we can see the various formulas that we have used to get the equations.
Hello sir, myself Shashank, and I'll be discussing about the simulation and the result part of this project. So this is the block diagram of the satellite which we simulated in the MATLAB Simulink. So as we can see, this is the vehicle model which we choose. It's a CubeSat satellite. We didn't change the satellite model. We just assumed it to be a CubeSat. And later we just change the mission configuration. As we can see, there's this values which has been given. We can change those values based on the requirements. And also this is the simulation. This is the simulation. Yeah, as we can see, the satellite is moving. So this was the path which we decided, and the satellite is tracking that. And we wrote a MATLAB code to get the rate of change of quaternions, Euler parameters, and these were the result which we got. And the thing is that we didn't add the control system part to the code, so we can see so much of variation in the plots as well. So this is the plot for various quaternions parameters with respect to time, and this is the angular velocity component. With variation with time along the time, and this is the Euler angle components.